Hello, everyone. Welcome to today's episode of Corecast. I'm your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Queercast. Unfortunately, our co-host Mikey won't be able to join us this time, but hopefully he'll be able to join us next time. So without further ado, let's get to it. Just a few logistical things to get out of the way. If you haven't already, do join our Discord channel so you can ask us questions there, and we can get to them as well. And then also, if you're on YouTube, please do ask questions while we're doing the episode, and we'll get to them as well. So, Tim, I guess like this, and also I forgot to mention, this is a part two of our whole quantum mechanical series. Before, or rather, or not a quantum mechanical series, just normal series. Before we talked about like fundamental things, and then we came across information. If you haven't already, check out that previous episode, see what is the most sacred thing in physics. Long story short, it's information, not energy, not momentum, and we delve into that in the previous episode. So, and then we talked about things like quantum information. Now, I wanted us to delve into like interpretations of quantum mechanics because it's very complex, very like just yeah, just really complicated stuff. So, Tim, what's a good like place for us to start in this discussion? Would you say?
Yeah, I think a good place is kind of tackle maybe some of those, a little bit of misconceptions people have with quantum physics.
Mhm.
Like, I think quantum physics is a very popular, general public topic. And there's this aura of mysteries of like, oh, the quantum world is so mysterious. Like, it's like anything that could possibly happen could happen. But somehow there seems to be this connection between quantum physics and the real world, right? Like in the subatomic world, things are so fantastical. Particles can go through walls, and unexpected things could happen, but somehow we don't see that in real life, right? Like, like I don't walk through walls. I don't jump to random places, teleporting left and right. Um, like what gives? And it turns out that even though it's not obvious, it comes down to how we interpret quantum mechanics. The interpretation really is how to link the theoretical with the everyday practical observations. So, so I would say first we have to understand like what those mysteries are first.
Gotcha. Yeah, so let me kind of walk through the different interpretations I learned back in undergraduate quantum mechanics. So the first one, if I'm not mistaken, is called the Copenhagen interpretation,
Mm-hmm.
and that has to do with what I believe is called the collapse of the wave function. So based on my understanding of it, it's like you have this probabilistic nature, and then you run some kind of experiment, you do a measurement, and the particle like goes into some state that you know. It can be a range of possible states, but then it just collapses on like one state that you measure. So, was that correct in my understanding the interpretation, or is there anything you want to add to that?
Yeah, I would say I I would say we should even make it even simpler than that.
Okay.
Like this is sort of like the introduction to quantum physics, and I wouldn't even say much more that it's not even much of an interpretation at all. It's just kind of like what is the most bare bone thing you can do and still understand quantum physics. And let me explain what that means, right? So in quantum physics, what you get at the end of the day when you compute something, you compute these probabilities, right? So imagine you
Mm-hmm.
have a quantum coin. You might discover that through these computation that this quantum coin, let's say, is 30% heads, 70% tails, right? But of course, in real life, you don't just observe probability. At some point, you actually take a look at the coin and discover that it's a heads, let's say, right?
Mm-hmm.
And remember, we said 30% heads, 70% tails, right? So, but then at some point, once you find out that it's heads, then it becomes definitively heads now. It's not just 30 or 70%, it's 100% heads because we just measured it, right? So the question is, quantum physics describes probability, but in the real world, ultimately, probabilities have to get converted to actual observations. So
Mhm.
so where does that happen? Right? And the Copenhagen interpretation is not so much just, it's not much of an interpretation at all. It just says that what you see is what you get. It says that at some point, somewhere along the line, when you have 30%, 70% probability, there's this sudden collapse of the wave function. And it doesn't really provide any context on how that happened. It's just that, hey,
Mhm.
it becomes 100% and 0% because you literally just measured it, right? So that it's almost like the bare bone, like something like it has to happen, but it doesn't explain why or what.
I see. I see. Are there, and so to me, it seems like it matches experiments. Are there any like major red flags about it that you're just like, no, this is not a robust interpretation of quantum mechanics?
Yeah, I mean, it's almost like imagine if you just ignore the word quantum for now, right? Imagine
Hmm.
someone gives you a prediction of a die, right? Like or a prediction of a coin flip, right? And before the prediction, it says that hey, it's 50-50 heads or tails. And then all of a sudden, you say the theory also predicts that hey, once you get heads, it's 100% heads. And then you kind of scratch your head and be like, well, you're kind of missing the middle part. How
Hmm.
how maybe you're flipping the coin, how the coin spins in the air and then lands on your fingers. So
Hmm.
naturally, when people talk about the Copenhagen interpretation, it feels like you're talking about the beginning and the end, but you're completely
Hmm.
missing the middle. You're like, hey, at some point, there's something that's going on, and if you look at like a coin toss in the real world, what that's missing is physics, right? You look at the rotation of the coin, the air molecules, right? Naturally, people thought that, hey, when you talk about Copenhagen interpretation, maybe we're really just missing something. Maybe there's this intermediate thing that we're just ignoring, and we're just saying, well, forget that. Let's just look at the beginning and the end. So in some sense, I would say it's kind of had this had this feeling of incompleteness to it, basically.
I see. I see. So it explains the beginning, explains the end, but completely misses the middle.
Exactly. Yeah.
Ah, I see. I see. Yeah, that's absolutely fair. Let's jump to another popular interpretation, the so-called many worlds interpretation. I'm not even going to try to explain that one. Maybe, I'll leave that to you, Tim, because you'll probably be able to explain it much more thoroughly than I can at the moment. But can you break it down from the get-go? Like, what is it?
Yeah. So this multi-world interpretation is one attempt to kind of fill into the middle. Like the Copenhagen interpretation is more like let's just forget about it. So that's why there's this famous quote from Feynman. It's this is sort of like the shut up and calculate interpretation, right? Like oh, because in the experiment you only see the beginning and the end. Forget about the middle. As long as the prediction matches the experiment, there you go. But the multi-world interpretation is sort of like, well, you know, let's try to bridge that gap. At some point we have many choices, many possibilities, and on the other hand, we only have one possibility. So in the multi-world interpretation, it's kind of a really rudimentary way of bridging that gap. It's just saying that, hey, actually, all these possibilities are kind of just branching off into their own worlds. So anytime there might be some decision happening, the world is split in some sort of, I guess, metaphorical way. Not really
Hmm.
specified, but it says that hey, the reason why we see 100% heads now after we check a quantum coin instead of heads or tails is because we are living in the world where heads is prevalent. And there could equally valid parallel worlds. We just don't happen to be living in it, right? And such a way that and in such a way that the universe has always gone through this branching, kind of like infinite possibilities, branching off and off and off and off. And then this sort of gives this really sci-fi mystique, mysterious feel to quantum physics. Yeah, so I guess that would be a quick summary of that.
I see. I see. I guess like how can one think about branching? That's wild.
Yeah, I think that's one of the biggest criticism of it, right? Like even though we kind
Uh,
of fill in the middle of what at some point probability becomes realized, we traded it for this mysterious notion of branching. And I don't think anyone has ever really come up with like what the hell is this branching? Like 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 first we have this mysterious change from uncertainty to certainty in the Copenhagen. Now we have this mysterious branching, which is the same crux kind of, right? Like between coming from uncertainty to certainty, all of a sudden it branches, and somehow like we're in one world versus another. Um, but of course, the punchline is that these branchings are physically unobservable because once you go on one branch, it's not like you can go to the other branch, right? So it's like for you, you're always in one branch, like you're just in this massive tree of branches, but then there are many, infinitely many other branches. Yeah, but there's no mechanism, right? Maybe every millisecond there's a new branch, or maybe infinitely many branches, right? Because
mhm.
there's infinitely many decisions happening in the world. But then you have to also ask the question, well, what does it mean? What do you mean by decision? Like, what's going on? So.
I see. So there's just a lot of it attempts to try to bridge the middle part, but
Mm-hmm.
it introduces so many more questions of like, what does branching mean? What point does the branching occur if you define branching? How many branches are there per like event? And yeah, how does it all just interconnect with each other? Is that is that fair?
Yeah, basically, you're trading one kind of really uncomfortable thing about quantum physics, I guess, with another almost equally uncomfortable. But at least we've kind of made a little bit of progress, right? This is an attempt to fill in the gap, right? Kind of like, what happens in the middle. So there is some progress there, but I would say it's still not totally complete, right? It's still unsatisfactory to some regard.
I see. I see. So then I guess let's I can't think of any other interpretations at the moment. What would you say is like one that goes even further? Is there one that even goes further?
Well, I would say there's one that's orthogonal, and this is called the Bohmian mechanics point of view.
Okay.
It's highly non-mainstream in physics, right?
Hmm.
And but I think in the interest of this topic, we should at least delve into it, right? The
Okay.
Bohmian mechanics point of view is that they totally reject the fact that the world is probabilistic. They're saying
Hmm.
that, hey, this is just a figment of our ignorance, a figment of our imagination. It's because we don't have enough information about the world, which is somewhat
Hmm.
sensible if you think about it. However, and then their goal is basically to say that, hey, guess what? Maybe the world is deterministic, and that there's these hidden forces that are driving the motions of particles. They call these the pilot wave. But then the
Hmm.
property of pilot wave is that, if you do, let's say you have a quantum coin and it flips heads, it
Hmm.
changes the pilot wave in such a way that that everywhere else in the universe feels that effect. So you get the quantum correlations right. So now the universe you trade. So basically you convert uncertainty, this probabilistic nature, with something that's certain. But then, of course, this certainty comes at a cost. It means that there's a lot of hidden stuff in the universe that we couldn't figure it out. You're hiding that probability into something hidden, and then somehow there's this mysterious pilot wave that covers all over our universe that's guiding and helping. It's like a invisible helping hand
Huh.
to give you this. It's like a random number generator, basically. Kind of like helping you, massaging to make things look probabilistic. I would say that part is going super duper far. It's like if you really don't like the fact that the universe is indeterministic, you can go that far. But again, you're sacrificing a lot. Um,
S- So is the crux of the theory that it's deterministic, but there's just so many hidden parts that it appears like it's non-deterministic?
exactly. Basically, there are these hidden gears that are like churning around to making decisions, but then we
Ah,
cannot measure them, so it appears non-deterministic. So, but I would say it's really an old school of thinking. Basically, these are kind of like if you really want to hold on dearly to the pre-quantum mechanical world where everything is deterministic, kind of you can in principle discover everything about the world. If you really hold dearly onto that, you might think that, oh, how can it be possible that the world is non-deterministic? Then you might be stuck with something like the Bohmian interpretation.
I see. I see. What's the issue with adopting that? Like, is it yeah? Like, are there any issues with adopting that?
Well, the the issue is that actually the Bohmian point of view, there's a lot of the theoretical reasoning behind it is that it's incompatible with many tenets, many dear principles of quantum physics. For example, in quantum physics, there's this notion of symmetry, and it also plays well with Einstein's theory of relativity, meaning that space and time are treated on the same footing. But in this
Hmm.
pilot wave, somehow the location of something plays a pivotal role. And then you have these guiding pivot pilot waves that are kind of, you know, playing around with the location coordinate of something. But then if you look at Einstein's theory, it says that, hey, like space and time are convertible, they're malleable, right?
Hmm.
They're not exact, kind of like, oh, you know the location here is relative. And then the pilot wave doesn't can't really accommodate that. People have tried really hard to kind of incorporate these modern ideas in theoretical physics into this Bohmian mechanics, and it just seems silly, right? And also think of it this way: the pilot wave is a helping hand to guide every single particle in the universe, right? But then
Yeah.
we know that in quantum physics, particles can come in and out of existence. And now this
Hmm.
concept gets even murkier. Well, at some point, the helping hand has to kind of back off, be like, hey, a particle disappear, and then a new particle can appear, be born out of the quantum field. Then what does it do? The helping hand suddenly realizes the new particle is there and make adjustment, and that's like kind of wacko, to be honest. So
I see.
yeah, so for those reasons, it's not really mainstream because it doesn't really give you very much, right? But then
Hmm.
you have to give a lot, right? You have to pay a hefty price just to just so that you have a deterministic world, which I think is silly.
Ah. Okay then. Then is all hope lost, Tim? What what's left?
I don't think all hope is lost. And indeed, in the I don't know how the history goes. Like in the days of modern quantum physics, I truly believe there's this new interpretation, a very modern interpretation. It's like this is the new hope, that and this idea is called decoherence. You may have heard of it. This is the gap between the beginning and the end for the Copenhagen interpretation.
Hmm.
And what's important is that well, at least the decoherence part, it has nothing to do with interpretation. It actually can be derived. It's a statement. It's actually a well tested principle. You can experiment with it, right? It's a statement, a principle that bridges the gap between probabilistic and deterministic, and the only thing you need are just the principles of quantum physics. It turns out you can just derive this principle out, and this
Hmm.
this concept is called decoherence, right? And I think from that you can really build a more modern kind of realistic way of viewing quantum physics.
Huh. So how does this work then?
Yeah. So one important thing to note is that is to understand, what is the crux, right? The crux is that in the real world we don't see inconsistency in our everyday objects. Like for example, my cup here. Um, Once I determine my cup is here, my cup is here. It's not going to suddenly shift, like teleport to the left and right, right?
Hmm.
These consistencies are kind of the important parts of our reality, obviously, right?
Hmm.
But this kind of consistency does not actually exist in the quantum realm when you zoom in, right?
Hmm.
So there seems like there's a gap, right? Um, but decoherence tells you that when you look at a quantum system that's really, really large, that contains trillions and trillions of interacting particles, it tells you that, imagine you start with an object, and let's say this object, the position of this object is kind of vague. It's probabilistic, right? It's either,
Hmm.
it's somewhere in the spectrum between left and right, somewhere in the middle, right? Okay.
Hmm.
Decoherence tells you that if you have a if you try to measure that, let's say you have a huge apparatus with many many particles, the state of the system will evolve in a way that it will the only thing you will observe are the consistent part. It's either on the left or on the right, but never in the middle, right?
Mm.
So that's how you can transition from something that's vague, that's kind of probabilistic across some spectrum, into something that's concrete. Be like, hey, it's either left or right, right? So that's what decoherence gives you.
I see. I see. So it gives you consistency of more macroscopic phenomenon. It's the reason we don't see like things kind of vanish from one part and go to another part.
Yeah, it's more like it's an amplification of consistency, right? So the idea is this: like imagine I have one particle, a quantum particle, that a quantum coin, right? That
Uh-huh.
could be heads or tails, right? And in the
Yep.
quantum realm is really a toss up. You don't really know, right? And then you can ask the question: if I measure, let's say if I have a device that measures it, and then I look at the device and then
Hmm.
communicate to you, Sahil, and you kind of write a paper to the world to say that, hey, we measure something, right? The, the coherence tells you that once the apparatus, let's say, measure that it's let's say heads, right?
Hmm.
Then I will also have a consistent measurement. I will see that the device sees heads, and when I
Hmm.
communicate to you, Sahil, you also understand that it's heads. And when you broadcast it to the world, it
Yeah.
it will be consistent that it's heads. There will be no ambiguity that maybe it was tails, right? So
Yeah.
so this is kind of the crux, I guess.
I see. I see. And does this depend on like observers themselves for this phenomenon to exist, in the sense like, is this a human centric phenomenon that we're macroscopic creatures, we observe things, so we interact with these like quantum systems or large scale systems in like, because we're also macroscopic?
Yeah,
Is there anything with that, or
yeah,
yeah?
yeah. These are excellent questions, right? And why they're excellent is because in the Copenhagen interpretation, somehow we put this heavy weight on an observer, right? Oh, when you observe something, somehow the uncertainty goes away, right? But in this
Hmm.
decoherence picture, it's a little different. The amount of decoherence you can actually measure, right? So humans have many many particles, so it's really good at decohering stuff. Like if you
Hmm.
if you use decohering as a word, meaning that I guess to define it, it kind of loosely means like making making something less and less quantum mechanical, kind of, right? And it
Hmm.
lies in a spectrum. The larger your apparatus, like imagine if your apparatus just has one atom or two, right? It's not going to decohere very much. Basically, the quantum mechanical property, or the fact that an object can be in between a spectrum, in between heads and tails,
Hmm.
it doesn't disrupt it very much. But the moment you add more and more, let's say molecules, it will disambiguate it more and more and more, right? And in fact, you can measure and go into the lab to measure how much decoherence there is. And people have published
Hmm.
papers, and it pretty much matches what you would expect. And it gets exponentially small, more and more. The ambiguity gets exponentially smaller and smaller the larger your observer is, basically. So going back to your question, no, it does not rely on the fact that humans are some conscious being. Like
Hmm.
any large apparatus can do this decoherence in terms of a measurement.
I see. I see. Uh, so actually, I want to ask you two questions. One's a little bit kind of like bit of a wacky sort of question.
Mm-hmm.
Like all of physics, as we know, is done from our conscious experience. So how do you know that it's outside of us that this phenomenon actually will occur? Is my question. It might be a bit of a metaphysics type of question.
Yeah, I mean it's not. I mean it's not insane, right? Like you could try to argue that hey maybe everything's a simulation, yada 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 yada, right? But
Hmm.
of course, in order to accept that, then you also have to accept that there's got to be some accounting going on. There's going to be some kind of accountant, like a program
Hmm.
that keeps track
Hmm.
of keeps track of every mind that exists. Of course, maybe you can take the selfish approach, be like, maybe Sahil, you are just some robot, and I'm the real conscious mind. I'm just like playing in this. But I feel like let's ignore that for now, right? Let's
Yeah,
assume
yeah, yeah.
this is a sociable. I think all the evidence suggests that we're pretty similar, right? So so from that perspective, if you were to believe that there's some overarching bookkeeping, keeping track of all the minds so that the universe run in this way, there's a lot of fluff, right? And if
Hmm.
you follow the principle of Occam's razor, like what is the more efficient way to get this done, it's much more likely that there just is a consistent framework in which we all live, and we all happen to live on it, and then there just exists one set of consistent information, as opposed to billions of consistent information being copied to everyone's heads. There just is one set
Hmm.
of truth that there is some mechanism to synchronize all these truths to each other through physics, right? Through information exchange, by Occam's razor, that just seems more reasonable, right?
Hmm.
I think certainly you can deal with philosophy and be like, oh, okay, I don't believe anything physics, science say, whatever. I mean, you can take that perspective, but it's way more productive to take the other perspective, that there's something simpler out there.
I see. That no, that absolutely makes sense. I guess the other thing is also no interpretation of quantum mechanics explanation wouldn't be complete without tying it back to the infamous Schrodinger's cat. So can you like explain decoherence, or rather Schrodinger's cat through the framework of decoherence?
Right. Yeah. And let me just give a caution that decoherence is a phenomenon. It's not an interpretation. Right.
Okay.
It's just is true. Decoherence just is true. I don't care what interpretation you have. Decoherence is a
Mm.
fact. It's a proven, well experimented fact. In fact, in quantum computing, this is one of the problems of quantum computing, because decoherence will screw up your quantum mechanical property. It'll screw up
Mm.
your quantum qubits. You don't want that, right?
Hmm.
But beyond that, the nice thing about decoherence is that it can give you a framework to create a better interpretation, and that interpretation
Mm.
is called consistent histories. Um,
Hmm.
but in this Schrodinger cat, let me explain. Right. So well, maybe we just describe the experiment a little bit, right, to our audience who are
Yeah. Go
unfamiliar.
for it. Go for it.
Yeah. So basically, the idea is this: imagine we have a cat in a box, like sealed in a vacuum, whatever. At least the cat stays alive, really well sealed up. And then there's some poisonous gas, and whether this poisonous gas is released or not depends on whether some radioactive decay happens or not, right? And let's say you
Hmm.
compute it, there's like a 50% chance this could happen or this could not. The question is, is the cat quantum mechanical? You know, if so, isn't it plausible that at some point the cat is kind of both dead or alive? Because in
Yeah.
quantum physics, you can have something kind of in the spectrum in between possibilities, right? That's what we're
Hmm.
describing, and that just sounds absurd. We've never seen cats that are either dead or alive. What is it, like a zombie cat? That just is crazy
Hmm.
nonsense, right?
Hmm.
Okay, and if you use the Copenhagen interpretation, it does sound crazy. It's like, hey, at some point, all of a sudden, the cat in the beginning is dead or alive, and all of a sudden it becomes dead or it becomes alive. That's sort of the Copenhagen interpretation, right?
Yeah.
The multi-world would just be like, there are many different worlds, and you happen to live in a world that the cat is dead or alive, and then world keeps splitting, more and more cats. You get infinitely many cats, I guess if you're a
I
cat
see.
lover, that might be okay. But right. And in the pilot wave, it's just like there's this invisible hand trying to, like it's like the cat's fate is kind of determined already, but we don't know. But there's some invisible hand trying to massage the poisonous gas and whether it releases or not. Okay, that's the Bohemian whatever, if you like, right? They all sound kind of
Yeah.
insane, right? But here's what really decoherence tell you. It tells you that because because in order for the cat to survive, it needs to have a lot of molecules. In fact, the cat has a lot of molecules, right? Okay,
Hmm.
so right from the get go, probably within trillionth of a second, something super tiny, the cat already has no quantum mechanical property whatsoever, right?
Hmm.
And what yeah. So basically, the air molecule has kind of already resolved the state of the cat. Okay, and let's consider what happened when, let's say, the poisonous gas is released or not. Right. Okay. Let's say there's some
Hmm.
quantum mechanical process, right? And then at some point, some trigger will happen, um, and then you have the state. The poisonous gas is either released or not, or somewhere in between. Okay, because there's a lot of apparatuses involved. Probably within the trillionth of a second, the gas is either released or not. They're basically two
Hmm.
branches, right? And both of these branches are completely realized, meaning that it's not possible for you to see, hey, the gas is released in 1 second, and the next second you'll be like, hey, the gas is not released. Mm-mm-mm. It
Hmm.
has to be consistent. Every millisecond you see the system again and again, it will be consistent. But decoherence doesn't tell you which path it's going to take. It just tells you that if you think of it as a probabilistic process, it will make sense, right? So basically,
Hmm.
even the millisecond right after the radioactive decay happened, the system has already decided, you know, the gas is released or the gas is not released, and then you just follow kind of the history, kind of the decision tree, kind of, right? So gas is
Hmm.
released, cat dies. Gas is not released, cat does not die. So at no point was there a cat that was dead or alive, basically,
Hmm.
right?
I see.
Yeah, there might have been a point at which the gas was, maybe not the gas, that the radioactive decay atom was decay or not decay, and we do observe that. Guess what? You look at subatomic particles, yeah, whether it's decaying or not, it's ambiguous. But then
Hmm.
the moment you zoom out and the more layers you peel off, it becomes more and more, less and less ambiguous. It got
I
disambiguated
see.
because of decoherence, right?
I see.
So,
That makes sense. I remember on the previous episode you talked about the unitarity being the most sacred law, it's the preservation of possibilities. So if one of these possibilities is realized by like the macroscopic world, what happens to the other possibility?
I think there we're getting the real juicy part, right? Decoherence only tells you. I think decoherence offers the most realistic, you know, um, interpretation. Well, of course, yeah. Okay. So if you observe the cat is alive, obviously the cat that's dead part, you you're basically completely inaccessible, right? It's gone, and
Hmm.
you can calculate it probably from decoherence. The probability of observing that is exponentially small, extraordinarily tiny. It's not zero,
Hmm.
right? But then yeah, you think of it in all the things that has happened in the world, there are all these possibilities, and because of unitarity, they never go away, right?
Hmm.
And so it smells a little bit like this multi-world interpretation. It almost feels like these
Hmm.
possibilities still live somewhere.
Yeah.
But if it's unitary, it still lives within our own universe, it turns out.
Hmm.
But it's just that the decoherence kind of propagate this consistent version of our world. And of course, then you can kind of question, well, like, what is reality, kind of,
Hmm.
right? Is it just a consistent history? I guess that's what the consistent history interpretation tells you. It says that
Uh-huh.
it's just a series of consistent history, which could have been which could have been other way.
Hmm.
Like that's the literal interpretation, but you can say maybe there's something else. But but I don't know. Like this is sort of beyond the interpretation now, obviously, and you could argue that that's the shortfall of this consistent history interpretation. But in my mind, I think out of all the possibility, this one is the best.
I see. I remember you mentioning it's probably the most realist uh, interpretation, consistent histories.
Right, exactly. So it's like there's no spooky invisible hand. There's no sudden collapses of wave function, or there are no weird branchings of our universe. Right? It's just that you know we are following one possibilities.
I see. I see. And no explanation of like why it chose that particular path.
Yeah, I think it's basically sort of like a leap of faith, to some extent. It's like, what is choosing a path anyway, right? If we truly believe the world is quantum mechanical, we should start with the assumption that it is quantum mechanical, and then
Mm,
see whether the world that we live in fits that description. And at the end of the day, what we perceive as probability, to some extent, it's just our way of approximating the world. So in some sense, maybe probability and determinism, I, you know what? Let me not say maybe. I think at the end of the world, determinism and probability, they are all approximations of our world, right? To
mm,
say anything else, I think you're fooling yourself. I think.
I see. I see. And then for the quantum mechanical aficionados out there, would you say that that decoherence is pretty much entanglement, quantum entanglement?
Yeah, you can reframe it that way. Decoherence
Mm,
is the entanglement. So you can kind of think of entanglement as a currency. It's a quantum correlation. Decoherence is basically the fact that this subtle the subtle correlation within a quantum system slowly leaking out into the environment and then realizing it to the rest of the world, right?
mm,
So you can frame it this way, and this is actually very solid experimental research. You can define it
I
in
see.
different ways and measure actually exactly how it works.
I see. I see. Yeah. All right. I think we're basically at time. Is there anything you want to say before we head out?
Yeah, I would say that yeah, I think a lot of confusion in quantum physics stems from the fact that there seems to be like this debate. There are all these different types of interpretation, yada 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 yada. But I truly believe that in the modern physics, we do have a much more coherent, maybe pun intended, pun not intended, of decoherence that comes in the picture, and it truly gives us a more realist view of quantum physics. And I think that's we're really getting a lot closer to what it really is.
Very nice. Very nice. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week for part three.
Yeah, thanks everyone. Bye.
Bye.